In this video, I'm going to talk about how we measure the curvature of spacetime mathematically. The three tools that we use to measure curvature on Riemannian and pseudo-Riemannian manifolds are the Riemann Curvature Tensor, the Ricci Curvature Tensor, and the Ricci Curvature Scalar. The Einstein field equations, which are the main equations in general relativity, contain the Ricci tensor and the Ricci scalar, so it's important to understand both of them. The Ricci tensor is also used in the curved spacetime description of Newtonian gravity, which is called Newton-Cartan theory, which I'll talk about in the next video. In this video, I'm first going to introduce these tensors, then at the end of the video, I'll show that the Rindler metric, used in the Rindler coordinate system for an accelerating observer in special relativity, describes flat spacetime, because all the components of the Riemann curvature tensor are zero. We'll see actual curved spacetimes with a non-zero Riemann tensor in future videos. And just as a warning, this video is going to cover a lot of content in a very short amount of time. If you feel lost after watching this video, you can check the description for links to my videos from my tensor calculus series, where I discuss curvature more slowly so it's easier to follow along. The video you're watching right now is basically a quick summary of these other videos. Remember, we are going to think of derivative operators as actual vectors, and we might write the basis vectors using any of these three notations. All of these mean the same thing. These are all derivative operators that are also basis vectors. Before the idea of Riemannian manifolds was invented, mathematicians like Gauss studied the differential geometry of 1D curves and 2D surfaces, which is sometimes called classical differential geometry. Gauss figured out that the curvature at every point on a 2D surface could be summarized by a single number, called the Gaussian curvature. At a given point, if the nearby surface could be approximated by two smiles, or two frowns, then that point had a positive curvature. If the nearby surface was made of a smile and a frown, it had negative curvature. And if the nearby surface had at least one straight line going through it, then the curvature was zero, meaning the surface could be unrolled into a flat sheet. Unfortunately, this approach with Gaussian curvature only works for two-dimensional surfaces. To understand curvature in any dimension, we need something called the Riemann curvature tensor. There are two ways to understand the Riemann tensor. The first is holonomy, which is the twisting of a vector when it's parallel transported around a loop. And the second approach is geodesic deviation, which measures the spread of neighboring geodesics in the manifold. In the last video, we said that to parallel transport a vector on a curved surface, we just march along a curve, keeping the vector as straight as possible. If we're at the north pole of a sphere, and we parallel transport a vector forward, sideways, and backward up to the original point, we notice that there's a change between the initial and final vectors. This change in the vector after parallel transport around a loop is called holonomy, and we can use holonomy to detect curvature. In flat space, like the surface of a flat table, when we parallel transport a vector around a small loop, the vector will be facing the same direction that it started in. Here there is no holonomy and therefore no curvature of the space. But if we parallel transport a vector around a small loop and find that the resulting vector points in a different direction, here we have holonomy, and we conclude the space must be curved. The Riemann tensor can detect holonomy like this. First we choose two vectors v and w and use them to make a parallelogram. Then we choose a third vector t to parallel transport around the parallelogram loop. The difference between t at the start and the end of the journey is a vector called r of v and w acting on t. Here, r is the Riemann curvature tensor. The Riemann tensor is a function that takes three input vectors, v, w, and t. Its output vector measures how much t has changed after it was parallel transported around the parallelogram formed by v and w. The formula for this output vector is shown here, and it's a bit complicated. We have three terms involving covariant derivatives of t. In the first two terms, we have the covariant derivatives in the directions of w then v, and then we subtract the covariant derivatives in the directions of v then w. You can think of this as parallel transporting our t vector along v then w, and then in the reverse directions of v then w to get back where we started. But then, what does this third term represent? Well, sometimes with vector fields, if we travel along v then w, and then from the same starting point travel along w then v, we end up at slightly different places. The gap between the two destination points is given by the Lie bracket of v and w, also called the commutator of v and w. This is given by v acting on w as a derivative operator, and then subtracting w acting on v. Remember, we're treating basis vectors as derivative operators, so the vectors v and w can be thought of as linear combinations of partial derivative operators. Now, I will admit that I've never seen a formal proof of this, but based on intuition, it seems like this third covariant derivative in the direction of the Lie bracket provides an extra vector that closes this gap in the parallelogram if it exists. One thing to note is that if the Lie bracket vectors are given by basis vectors from a coordinate system, then the Lie bracket always goes to 0. Algebraically, this is because the order of the partial derivatives doesn't matter. And geometrically, this is because the curves in a coordinate system always form nice closed grid boxes without any gaps at the corners. Since there's no gap, this indicates the Lie bracket is 0. When the Riemann tensor outputs the 0 vector for every single combination of inputs, this means that we never see holonomy. So we never see vectors twisting when we parallel transport them around a loop. So when a space is flat, the Riemann tensor will always output the 0 vector. If the Riemann tensor can output non-zero vectors, this means that the space is curved. Next, I'll talk about the components of the Riemann curvature tensor and its symmetries. Recall from Relativity 106a, to get the components of a covector alpha, we just get alpha to act on each of the basis vectors in our space. So alpha acting on the basis vector e mu gives the component alpha mu. Also, to get the components of the metric tensor G, we just have G act on a pair of basis vectors. So G acting on E mu and E nu gives us the metric components G mu nu. The Riemann tensor components are the same way. To get its components, we just have the Riemann tensor act on basis vectors E mu, E nu, and E sigma, and we get its components. Now remember, the Riemann tensor takes 3 vectors as input and outputs a 4th vector. So notice that since the output is a vector, we also have an extra upper index row that we use to sum with basis vectors, and this gives the output vector result. Also, you should notice that the Riemann tensor component indices are written in a bit of a strange order. The last 2 indices correspond to the 2 vectors we used to make the parallelogram. And the first lower index corresponds to the vector being parallel transported around the parallelogram. Different textbooks might use different conventions for the order of these indices, but this convention is the most common convention that I've seen. Now again, recall that covector inputs are linear. So we can either add input vectors or add the outputs and we'll get the same result. This also applies for scaling. We can scale the input vector or scale the output by the same amount and get the same result. These two properties together mean we can always pull coefficients from vector summations outside the covector input. This linearity property is true for all tensor inputs, including the metric tensor inputs and the Riemann tensor inputs. This means that to get the result of the Riemann tensor acting on any three vectors, we can write each input vector as a linear combination of basis vectors, and then bring all the scaling coefficients and summations outside. And since this is the Riemann tensor acting on basis vectors, we can just rewrite it as the Riemann tensor components. Now, to get an actual formula for the Riemann components, we'd need to put basis vectors into this formula. As I stated before, the Lie bracket goes to 0 for any basis vector inputs. And the rest of the result becomes this big ugly formula. The important thing to notice is that this formula only depends on the connection coefficients and nothing else. So the curvature of a space is completely defined by the connection coefficients. The full derivation for this formula is in Tensor Calculus video 23, which is linked in the description. If all of the Riemann tensor components are 0, this means that the space is flat. But if any of the components are non-zero, this means the space is curved. So the Riemann tensor components have one upper index and three lower indices. In four-dimensional spacetime, each of these four indices can have one of our four spacetime variables. This means that we have 4 times 4 times 4 times 4 equals 256 components in the Riemann tensor, which is a lot. Thankfully, we don't need to actually calculate all 256 of them. You already know that the spacetime metric is a 4x4 matrix with 16 elements. However, the matrix is symmetric, and G mu nu equals G nu mu. So 6 of the entries are just repeats of the other entries. This means there are only 10 independent components of the metric tensor matrix. The Riemann tensor components also have a number of symmetries between its four indices. And it turns out in 4 dimensions, out of the 256 components, there are only 20 non-zero components that are independent. The other components are either 0 or can be determined from the original 20. In 2 dimensions, where the Riemann tensor has 2 times 2 times 2 times 2 equals 16 components, it turns out there's only one independent non-zero component. The first of these symmetries says that when we swap the third and fourth indices of the Riemann tensor, we get the same component number but with a negative sign in front. The reason this is true is because the third and fourth tensor indices correspond to the two vectors we use to make the parallelogram loop that we parallel transport around. If we swap these two vectors, this corresponds to going around the loop in the opposite direction, which means that the parallel transported vector gets twisted in the exact opposite way. So the output vector points in the opposite direction, meaning it is the negative of the original output vector. You should also notice that this index symmetry means that if the third and fourth indices are repeated, the component is equal to the negative of itself, which means the component is equal to 0. So the symmetries of the Riemann tensor components force some of the components to be 0 automatically. You can check the description for Tensor Calculus video 23 for full proofs of all of these symmetries. You might notice that the Riemann tensor is written with 4 lower indices here. This is a shorthand notation for a summation of the Riemann tensor with the metric tensor, and is called lowering an index. We can re-raise the index by doing a summation with the inverse metric tensor. My Tensors for Beginners video 16 talks about raising and lowering tensor indices in more detail. Before moving on, there's a second interpretation of the Riemann tensor, called geodesic deviation, where the Riemann tensor measures how much a family of geodesics that start off close together spread out over space. Remember, a geodesic is defined as the path we get when we parallel transport a vector v along itself. Or in other words, saying the covariant derivative of v in the direction of v is 0. So let's say this collection of curves are all geodesic curves. So v is a vector field that's tangent to all these geodesic curves. Let's also say that this dashed line indicates the 1 second travel mark for all the geodesics. And this is the 2 second mark and the 3 second mark. The tangent vectors t on these dashed curves give an indication of how much these geodesics are separated from each other. These geodesic curves and separation curves form a set of grid boxes, kind of like a coordinate system. So the Lie bracket of v and t is 0. Now let's take our geodesic equation and take the covariant derivative of both sides in the direction of t. The right-hand side just stays 0. Then we'll add and subtract this term. The first 2 terms are exactly equal to the Riemann tensor of t and v acting on v. The third term in the Riemann tensor definition involving the Lie bracket goes to 0, since we said that the Lie bracket of t and v goes to 0. So this represents parallel transporting v around a parallelogram formed by t and v. Also, in this term, we can actually swap the order of v and t. This is because of the 0 Lie bracket, and also because of the torsion-free property of the connection. I explain the complete reasons for why we can do this swap in my tensor calculus video number 21. So we end up with 2 covariant derivatives of the separation vector t is equal to the negative of this Riemann tensor term. Since the vector t tells us about the separation between the geodesics, this means that the Riemann tensor can tell us how fast geodesics are spreading apart due to the curvature of the manifold. As an example, if we're looking at the surface of the moon, if we started 2 geodesics pointing north on the moon's equator, and then watched them travel over time, they would get closer and closer together because of the curvature of the moon's surface. So on curved manifolds, geodesics can come together or spread apart, simply because of the curvature of the manifold. This is how gravity, which is the curvature of space-time, can cause objects to naturally come together without any forces. Geodesics in space-time can just naturally converge together due to the curvature of the space-time manifold. Another tensor describing the curvature of a manifold is the Ricci curvature tensor. The Ricci tensor can be thought of as a kind of summary of the Riemann tensor. If you recall from linear algebra, we get the trace of a matrix by adding up all its diagonal elements. This means doing a summation over a matrix with itself, where the 2 indices are the same. The trace basically summarizes the matrix as a single number. The Ricci tensor is sort of like the trace of the Riemann tensor. We sum the Riemann tensor with itself using the top index and middle lower index as the summation indices. As a result, we summarize the 4x4x4x4 elements of the Riemann tensor as a 4x4 matrix called the Ricci tensor. The Ricci tensor is symmetric, so there are really only 10 independent elements. You might wonder why we sum with the middle lower index and not the lower left or lower right indices. It turns out that summing with the lower left index just gives 0, and summing with the lower right index just gives the negative of summing with the middle index. So doing those summations don't give us anything new, and we just ignore them. The physical interpretation of the Ricci tensor is that it keeps track of how a volume changes along geodesics. For example, in 2D space, we can make a square out of the vectors v and w, and see how its area changes as the corners travel along geodesics. Or in 3D space, we can see how a cube made out of vectors v, w, and t changes volume as its corners travel along geodesics. The Ricci tensor is a function that takes two vectors and outputs a scalar. If v is a unit vector, when we put in the same vector v twice, the resulting scalar is called the Ricci curvature. The Ricci curvature is a bit like a constant of proportionality that helps relate a volume and its second derivative rate of change in the direction of v. I'll explain how to visualize this. Let's say that we pick a direction v and we look at how geodesics change along this path. If the geodesics converge together, then this circle living in the plane of the basis vectors e1 and e2 will get smaller as it travels along the geodesics. This means the space has positive Ricci curvature along the direction v. If the geodesics diverge apart, then the circle will get bigger. This means the space has negative Ricci curvature in the direction of v. If the geodesics don't diverge or converge, then the circle stays the same size and we have 0 Ricci curvature in the direction of v. Now, something to keep in mind, we might run into a case where some geodesics converge, but other geodesics diverge. And the circle will get squashed smaller in one direction, but stretched bigger in another direction. But overall, the area will stay the same. In this case, the Ricci curvature in the direction of v is also 0, because the area of the circle has not changed. The Ricci tensor can only detect changes in area or volume. It cannot detect changes in shape. Here, even though the shape of the circle has changed, the overall area has not changed, so the Ricci curvature here would be 0. So this is a very important point. The Ricci tensor being 0 does not mean our space is flat. We can have a 0 Ricci tensor and still have a curved space. A 0 Ricci tensor simply means the curvature of space doesn't result in volume changes when we move along geodesics. But the curvature of space can still cause changes in shape when we move along geodesics. The last way of measuring curvature is the Ricci curvature scalar. We get this by raising one index of the Ricci tensor and then summing over the top and bottom indices to get a scalar. In flat space, a circle of radius r has a circumference of 2 pi r and an area of pi r squared. But in curved space, like the surface of this sphere, a circle with the exact same circumference can actually have a larger interior area, because the curved surface of the sphere causes the area to bulge out. So in curved spaces, a circle can have an area that's bigger or smaller than pi r squared due to the curvature of space. A positive Ricci scalar means the circle in curved space has more area than a circle in flat space with the same circumference. This also means a circle in curved space has less area than a circle in flat space with the same radius, if we're measuring the radius as the walking distance from the middle to the edge of the circle. A negative Ricci scalar means the opposite. A circle in curved space has less area for a given circumference and a larger area for a given radius than we would expect in flat space. And a zero Ricci scalar means the area of a circle is exactly what we would expect in flat space, pi r squared. So looking at the Einstein field equations, we see that the left-hand side contains the metric, Ricci tensor, and Ricci scalar. The left-hand side of the Einstein field equations is all about geometry and curvature. In the next couple videos, we'll talk about the right-hand side, which is about mass, energy, and momentum. The last thing we'll do in this video is prove that the Rindler metric describes flat spacetime. Recall from Relativity 105 Part B, the Rindler coordinates ct tilde and x tilde are a spacetime coordinate system for an accelerating observer with constant proper acceleration alpha. This observer travels along a hyperbola that's a constant proper distance of capital D equals c squared over alpha from the origin. If you recall, when we looked at a collection of accelerating spaceships, all separated by a constant proper distance of d from each other, the clocks on each spaceship would tick at different rates. Spaceships farther from the origin would have clocks that ticked faster. We were able to calculate the proper times of each ship using the Rindler metric from Relativity 105D. The Rindler metric is just the dot products of the basis vectors in Rindler coordinates, and this helped us measure proper times along curves in the Rindler coordinates. We can determine the curvature of spacetime in the Rindler coordinates using the following procedure. We start with the metric for the coordinate system, then we calculate the connection coefficients using the Levi-Civita connection formula from the last video. Then we calculate the Riemann curvature tensor and then use that to get the Ricci tensor and scalar. So we start with our Rindler metric, which is a matrix of the spacetime basis vector dot products. I'm assuming there's no motion in the y and z directions, so we're going to ignore y and z and just look at the 2x2 metric tensor matrix for time and x. And recall, G with upper indices is just the inverse metric matrix, which sums with the ordinary metric to give the Kronecker delta. Since the Rindler metric is diagonal, we can get its inverse matrix just by taking the reciprocal of the diagonal elements in the ordinary metric. Next, we take the formula for the connection coefficients. Remember, because the mu index appears up top and down low, there's a summation over mu going on, from 0 to 1. We can also think of 0 as being the spacetime index for time, and 1 as being the spacetime index for x. The connection coefficients have 3 indices. If we're using t and x, this means that there are 2 times 2 times 2 equals 8 total coefficients. It will turn out that a lot of these terms and coefficients go to 0, so we're going to use some tricks to find these 0 terms and get rid of them. We're going to look at 2 separate cases for the coefficients. In case 1, the alpha index will be t, and in case 2, the alpha index will be x. Let's look at the alpha equals x case first. The only way the inverse metric is non-zero is if mu equals x as well. So we replace mu with x and ignore the t part of the summation. You can check that the first 2 derivatives go to 0, regardless of which values we use for nu and sigma. And this last derivative is only non-zero if both nu and sigma are both t. So we have a formula for the xtt Christoffel symbol. The xx component of the inverse metric is -1. and GTT is x tilde over d all squared. The derivative of x tilde squared is 2x tilde, and canceling the 2 and the 1/2 and the minus signs, we get a value of x tilde over d squared. All the other Christoffel symbols with x up top go to 0. Now let's look at the alpha equals t case. The only way the inverse metric is non-zero is if mu equals t as well. So we replace mu with t and ignore the x part of the summation. This third derivative with respect to time goes to 0 right away, since the metric does not depend on t tilde at all. For the remaining two indices, the choices that give us non-zero results are either nu equals t sigma equals x, or nu equals x sigma equals t. But these give the same connection coefficient result, since swapping the lower indices doesn't change the value. Let's use nu equals t sigma equals x. G inverse tt becomes d over x tilde all squared, and gtt is x tilde over d all squared. After taking the derivative, we cancel the d squares, cancel 1/2 with 2, and cancel one factor of x tilde to get 1 over x tilde. All the other connection coefficients with t as the upper index go to 0. So we find with Rindler coordinates, only 3 of the 8 connection coefficients are non-zero. These are the exact same results we got in Relativity 105 Part E, except this time we got the results straight from the Rindler metric, and we didn't make use of any other coordinate systems. Now let's compute the Riemann tensor components. Remember, in 2D, there's only one non-zero component that determines all the others. So let's choose the tx component. If we remember the connection coefficients we just calculated, we can sub in gamma xtt and gamma txt. With the other two summations, we need to find values of sigma that result in non-zero results. The first sum goes to 0 for both choices of sigma equals t and x. The second sum is non-zero if we choose sigma equals t, and we get 1 over x tilde times 1 over x tilde. So the first derivative goes to 0 since there's no time dependence. The derivative of 1 over x tilde with respect to x tilde is negative 1 over x tilde squared. And this cancels with the 1 over x tilde squared in the last term, so we get 0. So since the tx component of the Riemann tensor is 0, using the symmetry rules, we find that all components of the Riemann tensor are 0. This means that the Rindler metric describes flat spacetime, as expected. This also means that the Ricci tensor components and Ricci scalar are also 0. So to summarize this video, we learned about 3 ways of measuring curvature: the Riemann tensor, the Ricci tensor, and the Ricci scalar. We can interpret the Riemann tensor as measuring holonomy, which is the twisting of a vector when we parallel transport it around a loop, or as a measure of the spread of nearby geodesics. When spacetime is flat, this is the same thing as the Riemann tensor being 0. The Ricci tensor is like the trace of the Riemann tensor, and it keeps track of volume changes due to curvature as a volume travels along geodesics. When the Ricci tensor is 0, it tells us that volumes don't change due to curvature. But it's still possible for space to be curved even if the Ricci tensor is 0. And the Ricci scalar tells us if the area of a circle of a given circumference is more or less than we'd expect compared to a circle in flat space. In the next video, we're going to use the Ricci tensor to describe the curved spacetime of Newtonian gravity.